Imagine holding a solid piece of material that refuses to conduct electricity through its bulk, but allows electrons to glide along its outer skin. Not through a wire attached to it. Not through a coating added later. The surface itself becomes the highway. Inside, the material behaves like an ordinary insulator, blocking electrical motion. But at the boundary, where the material meets air, vacuum, or another ordinary material, conducting states appear almost as if they are required to exist. This is the central surprise of a topological insulator. It is not simply a conductor with a bad interior, and it is not simply an insulator with a dirty surface. It is a distinct quantum state of matter where the deep structure of the electron bands forces the edge or surface to conduct. The strange part is that the surface conduction is not an accident. It comes from topology, the mathematics of properties that cannot be smoothly changed without a break. To understand why this is strange, start with an ordinary insulator. In a solid, electrons occupy allowed energy bands, and between those bands there can be forbidden energy ranges called band gaps. If the highest filled band and the next available band are separated by a large enough gap, electrons cannot easily jump into mobile states. That is why materials like glass or rubber do not normally conduct electricity. A topological insulator also has a band gap in its interior, so from the inside it looks perfectly insulating. If you only measured the bulk, you might think nothing special was happening. But the difference is hidden in the shape and relationship of the bands themselves. In a topological insulator, the valence and conduction bands are arranged in a way that is informally described as twisted compared with an ordinary insulator. That twist is not visible like a knot in a rope, but it has real physical consequences. Topology is about what stays the same when something is smoothly stretched, bent, or deformed without being cut or torn. A coffee mug and a donut are famously similar in topology because each has one hole. A sphere and a donut are different because you cannot turn one into the other without closing or opening a hole. In topological materials, the same idea applies to electron band structures rather than everyday objects. A trivial insulator and a topological insulator may both block current inside, but their band structures belong to different topological categories. You cannot smoothly transform one into the other while keeping the insulating gap open the whole time. Somewhere along the transformation, the gap must close, and when the gap closes, conducting states appear. That forced transition is the clue that the two materials are not merely variations of the same thing. They are separated by a deeper kind of order. Now picture a topological insulator placed next to a trivial insulator, or simply sitting in vacuum. Vacuum is topologically trivial for this purpose, so the boundary separates two regions with different topological character. The bulk of the topological insulator cannot smoothly become the outside world without crossing a change in topology. Because the band gap cannot remain quietly open through that boundary, nature supplies conducting states at the interface. This is why the surface or edge becomes conductive. It is not because the surface is contaminated or because atoms there happen to form a convenient pathway. It is because the boundary is where two incompatible topological phases meet. The conducting surface states are the physical bridge between them. In two-dimensional versions, these appear as edge channels. In three-dimensional versions, they form conducting surface states spread over the outer faces of the material. The most important feature of these surface states is their robustness. Ordinary materials can also have surface conduction for ordinary reasons, dangling bonds, impurities, defects, or chemical changes at the surface. But those states are fragile. A scratch, impurity, or small disturbance can often localize or destroy them. Topological surface states are different. As long as the key protecting symmetries remain intact and the bulk gap stays open, local disturbances cannot simply erase them. A little disorder on the surface does not remove the underlying topological mismatch. The conducting channel is protected by a global property of the entire band structure, not by a delicate local arrangement. That does not mean topological insulators are invincible or perfect conductors in all conditions. Strong symmetry breaking effects, magnetic disturbances, or structural changes can alter their behavior. But within the right conditions, their surface conduction is unusually resistant to ordinary disruption. A formal way to define a topological insulator is this: it is an insulating material that cannot be adiabatically transformed into an ordinary insulator without passing through a conducting state. Adiabatically, in this context, means changing the system slowly and smoothly while preserving the relevant conditions. If the material were trivial, you could imagine gradually adjusting parameters until it became another ordinary insulator without anything dramatic happening. But with a topological insulator, the path is blocked. The only way from the topological phase to the trivial phase requires the energy gap to close at some point. That gap closing creates conduction. This means topological insulators occupy distinct regions in a phase diagram, separated from ordinary insulators by conducting phases. They are not described by the older and more familiar Landau picture of matter, where phases are usually distinguished by symmetry breaking, such as a liquid becoming a crystal. This makes topological insulators part of a broader story in modern physics. Not all phases of matter are defined by visible order. A magnet is ordered because many spins align. A crystal is ordered because atoms repeat in space. But a topological insulator can preserve the same apparent symmetries as an ordinary insulator while still being fundamentally different. Its distinction is encoded in global quantum properties. These phases are often called symmetry-protected topological phases because their special boundary states depend on certain symmetries being preserved. One common symmetry is U1 symmetry, linked to particle number conservation. Another very important one is time reversal symmetry, which roughly means the laws look the same if motion is reversed, as long as no magnetic field breaks that condition. The combination of dimension and symmetry determines which topological phases are possible. In some cases, topology allows protected states. In others, it forbids them entirely. Physicists classify topological insulators using mathematical quantities called topological invariants. These invariants act like labels that identify whether a material belongs to a trivial or topological category. Some take integer values, often represented by z. Others take values in z2, which means there are essentially two possibilities, like even or odd, trivial or non-trivial. These labels are not arbitrary names. They summarize deep information about how the electron wave functions are arranged throughout momentum space. If two materials have different invariants, they cannot be smoothly connected without closing the gap. This classification has led to what is sometimes called the periodic table of topological insulators, which maps which topological phases can exist depending on spatial dimension and symmetry class. It is a periodic table not of elements, but of possible quantum behaviors. It tells researchers where to search for protected edge and surface phenomena. One of the most striking features appears in three-dimensional topological insulators with time reversal symmetry, spin momentum locking. On the surface, an electron's spin is tied to the direction it moves. If the electron moves one way, its spin points in a related direction, often at a right angle to its momentum. If it reverses direction, its spin would need to change as well. This matters because ordinary scattering often involves electrons bouncing backward after hitting impurities or defects. But in these surface states, a simple U-turn is strongly suppressed because the backwards moving state has a different spin structure. Unless something can flip the spin in the right way, the electron cannot easily scatter straight back. The result is surface conduction that can be unusually metallic, even though the interior remains insulating. This does not eliminate all resistance, but it changes the rules of electron motion in a remarkable way. This also explains why topological insulators attract interest for future technologies, even though practical applications are still challenging. Robust surface conduction, spin momentum locking, and controllable boundary states are valuable ingredients for spintronics, low-dissipation electronics, and quantum devices. Spintronics aims to use electron spin as well as charge, and topological surfaces naturally connect spin and motion. In quantum computing research, certain topological materials may help create exotic quasiparticles or protected states that are less sensitive to noise. However, real materials are messy. The bulk may not be perfectly insulating. Defects can add unwanted carriers. Surfaces can react chemically. Fabricating clean samples and controlling their environment is difficult. So the promise is not that every topological insulator immediately becomes a miracle device. The promise is that topology gives engineers and physicists a new design principle: build functionality from global protection instead of fragile local perfection. The idea has also moved beyond electrons in solids. Researchers have created analogs of topological insulators in photonic systems, where light travels along protected paths, in acoustic systems, where sound waves move around defects, and in magnetic or mechanical systems with topologically protected modes. These examples show that the core concept is not limited to one material or one particle. What matters is the wave structure, the symmetry, and the topological distinction between phases. If a system supports waves and has the right kind of band structure, it may be possible to engineer edge modes that resist backscattering or disorder. This is why topological physics has become a language across many fields. It allows scientists to ask a powerful question: can the global shape of a system's allowed states force waves to travel safely along a boundary? So the simplest definition is still the best starting point: a topological insulator blocks current inside but conducts on its surface. The deeper explanation is that its electron bands carry a topological twist that ordinary insulators do not have. That twist cannot be removed smoothly without closing the energy gap, and when the material meets a trivial region, the boundary must host conducting states. These states can be protected against many local disturbances, and in important cases they display spin momentum locking, where the direction of motion and spin are inseparably linked. Topological insulators matter because they reveal a form of order that is not based on broken symmetry or obvious structure, but on global quantum geometry. They show that two materials can look similarly insulating in the bulk while belonging to fundamentally different worlds. The surface is where that hidden difference becomes visible. If you found this helpful, please like this video and subscribe for more explainers.